So I think we are ready to start our third presentation for the school, which is going to be presented by Professor Valentina, and it will be a great way to close the school today because she will give us a vision of, well, wireless power transmission is interesting, but can we use it for doing something in other fields? So she will show us some sensors and things like that. She's coming from University of Perugia in Italy. So Valentina, if you want.
Thank you very much, Nono, for the introduction. Hello, everybody. My name is Valentina Palazzi, and as Professor Carvalho said, I'm from the University of Perugia in Italy. My talk will be about developing a particular type of wireless sensors, that is harmonic tags, and I'll show you how I came up with this research area. So the area where it's where the research field that we are addressing with my talk is wireless sensors. And why we need wireless sensors is because sometimes we want to monitor things that are moving. Here I reported an example of industrial applications, but for instance, this is also applied to humans. If you want to monitor vital parameters or stuff like that, we cannot be attached to the grid. So every time we have mobile platforms, or every time we need to monitor remote equipment, which is maybe distributed over extended areas, having sensors, transducers that are connected with cables to some reader can be quite inconvenient. Therefore, we need wireless sensors, which means that we not only have to take care of the transducer, but also to assist them to transmit this data wirelessly, which is a bit challenging. This is challenging because usually when we are thinking of different applications, for instance, industrial applications, environment is not optimized for electronics. So we have to put these electronics in environments that can be characterized by high temperatures, where humidity is not controlled. And the problem is that sometimes we cannot do maintenance. Maintenance to replace sensors if they are not working, but also, for instance, to replace batteries, which was basically the topic that Professor Carvalho was addressing this morning. To develop wireless sensors, we can use, here I made this classification between active and passive devices. With active devices, I mean a device which has, let's say, an oscillator, an RF oscillator on board. So this means that the power must come from a battery, or at least we need to provide, some power source on board. This approach, for instance, I'm thinking of some commercial applications like Bluetooth Low Energies, Wi-Fi, Zigbee, are protocols that are used for active wireless transponders. This approach can be attractive because with research we are moving towards low power electronics, which means that battery can last a lot of time. So in some applications this is good, and we can also develop solutions based on energy harvesting, not only RF, but for instance, thermoelectric generators, piezoelectric energy harvesters, and so forth. And of course, these devices where you have the sensor and it is usually connected to a microcontroller unit and the information is sent allows us to have more functionalities. So we can have also multi-sensor platforms. And usually you have longer read ranges. Probably LoRa solutions are the best example for that, because you can apply them for instance, remote control of precision agriculture, and you can reach kilometer ranges. So this is very good. On the other hand, I put passive devices. Of course, passive devices are not passive in the sense that to receive some information you need to provide some power, but they are usually powered by a reader, so they are powered by RF. And these devices do not have any, usually they don't have any power source on board. These devices are more robust because they usually are, they are not switched on, they're off. So for instance, you activate the electronics only when you intend to read the data. So they are more robust to, let's say, difficult environmental conditions. And you can make them today we will see a lot of low complexity solutions, which also improve their reliability in the end. So they have some, positive things. Of course, usually read ranges are lower, and you have to, let's say, minimize the functionalities that you want to add. Otherwise, you need an energy source. So here I reported a scheme of the system. As I said, you have a tag that doesn't have any energy source on board, and you have a reader. The reader transmits carrier at RF frequencies. Usually, you can have even near field applications. For instance, I'm thinking of the NFC solution, or usually you have they work in the far field. You have the reader that transmits a continuous wave signal, or at least an RF signal, and then the tag reflects back this signal. And usually it encodes the information in the modulation of the reflected signal. So the reader basically analyzes the signal that is backscattered by the tag, that is reflected back by the tag. And by analyzing the amplitude modulation or the phase modulation or even the frequency modulation of the received signal, it gathers this information. So these kind of solutions can operate even in harsh environment, as I said. Usually this means also that you have reduced waste because they are, very small, and usually they rely on a small number of components. So even if you have to, dispose them, this is more convenient. Here I reported the scheme, the basic scheme of a commercial solution, which is, I don't know if you are familiar with, but they are the UHF RFID solutions. I don't know if you ever, went to a place, you bought some things and you didn't have to scan the barcode, but for instance, in Italy, we have this the Decathlon. You put all stuff inside a box and they just, tells you how much you have to pay. In the how do you say, the label that you have on your clothes, there is a chip usually, which is a UHF RFID chip that works like this. This is passive. Usually it is switched off. It doesn't work, but it has an antenna working around in the US. I think it's 915 megahertz. In Europe is 868 megahertz. And basically it has a rectifier. So the RF power that is sent, for communication, it is also used to power the sensor. And this rectifier provides DC power, which is used to switch on a very, low power and low voltage processor. And this processor basically, and also usually it is also equipped with memory, flash memory. And this sensor, this processor activates the transmitter, which is basically, it provides a signal to switch on and off a MOSFET. And when the MOSFET is switched off, basically this antenna is matched over 50 ohm, so no power is reflected back. While when the MOSFET is switched on, this means that the antenna is short-circuited, and so all power is reflected back. So basically you are modulating the amplitude of the reflected signal. And usually the impinging signal can also provide some information, some requests. And so it is not just a pure continuous wave signal. So you also have a demodulator, you see here. And this demodulator basically is providing which kind of information should be sent back by the tag to the reader. This usually works very well when you have to provide a static information. So as I said in the retail, every label is equipped with a specific code, and this is a static information. This doesn't change over time, and it is stored in the memory. And the question is just give me your ID, and the ID is sent. And this can work passively. The reader, which transmits at most 36 dBm, can read tags up to 10 meters. So it's quite a good solution. The problem is that if we want to add sensors, as I did here, there are some RFID that you can find on the market that has some integrated sensors, or they have some ports where you can add a sensor. You have to also acquire this information, and so this means that you need an analog to digital converter, which is usually a little bit more power hungry. And so this means that you need more power, because we only have this RF signal that is used both for communication and for to provide power. So the point is that usually this solution can only work in a very limited range, or you anyway need an external source. Here I reported this energy source that can be a battery, but can also be a solar cell, or as I said, an energy harvesting solution, and that is used to power a wake-up circuit and to make this processor acquire the information from sensors. Another, let's say, drawback that you can have with conventional UHF RFID systems is that let's imagine that we transmit a sinusoid. In the frequency domain, this means that you have a spectral line, but in reality, you never have a spectral line. You have, the phase noise makes the spectral line a little bit larger, right? And the point is that if you are in an environment, like for instance, I'm thinking of industrial applications, which is where I work more, you have a lot of metal, you have a lot of reflections. This means that your reader is not only receiving the signal that is backscattered by the tag, but is receiving a lot of reflections from the environment at the the frequency corresponding to the interrogating signal. So the point is that if your backscattered signal is applying amplitude modulation, which is usually also not very high frequency. So for instance, UHF RFIDs at most achieve 128 kilobyte per second. So usually, you will want to waste power, so you are very slow in applying this amplitude modulation. You have these sidebands that occur very close to your fundamental signal. What can happen is that this phase noise basically is so high, because the reflection is very, very high, that you cannot really read very well the information that is provided by your tag. This is called self-jamming, and this is a possible issue that you can have with commercial UHF RFIDs in particular environments which are which has a very strong clutter. And so this limits the sensitivity of your receiver. So the idea of harmonic transponders is basically to separate the bands. You transmit your interrogation signal, of course, at one frequency, and your so downlink occurs at that frequency, and the uplink, of course, at another frequency, which is usually a harmonic of the fundamental one. So here I reported a very simple scheme of harmonic system. The reader, as I said, transmits a sinusoidal signal. Here you can see it's a spectral line. This signal is gathered by the input antenna of the tag. The tag is equipped with a frequency doubler, so it generates the second harmonic, and the second harmonic is transmitted back, and it is acquired by a reader, which is tuned to 2F0. Since F0 and 2F0 are very separate, and since your receiver can be tuned to 2F0, basically you don't care if there is a lot of clutter occurring at F0. So if there are a lot of a lot of clutter that is causing strong reflections at F0. This is the link budget analysis that they reported here. It's a very simple calculation that basically tells you what power at the second harmonic you can expect if you are transmitting a certain power at the fundamental frequency, and it is considered for the very simple case of free space propagation. So in reality things are a bit worse. As you can see here, so first of all, you are losing some power because the downlink is happening. So you're losing 6 dB because the downlink is happening at the second harmonic. And you also have to take care very carefully of this conversion loss here, which is reported as CL, which is basically the efficiency of your harmonic generation. So it basically is the ratio between the power that you are generating at the second harmonic with respect to the power that you have at the fundamental frequency. So basically the point is you are, of course, nothing comes for free. So you are increasing, let's say, your robustness to clutter, but you're losing some power because you have this complexity of the second harmonic generation. On the other hand, if you design your transmitter in a, let's say, in a smart way, let's say, if you have a transmitter that is a poor sinusoid, or if you take care adequately of the eventual nonlinearities of your transmitted signal, you can improve the sensitivity of the receiver a lot. So this is, let's say, the trade-off that you can consider. So the next point is understanding how to generate this second harmonic without relying on maybe bias, because the point is we want to avoid bias if possible. There are different approaches. I reported here some literature. One solution is to use nonlinear transmission lines. This is very interesting. So basically you have a transmission line, which is, a lumped, can be seen in a lumped version as an inductor, series inductor, and parallel capacitors. You can implement the parallel capacitors as varactor diodes. They are nonlinear. And so if a signal passes through this nonlinear transmission line, it generates harmonics. Or you can use single port reflection type frequency doublers. Here I reported a work from the group of Simon Hammer in France. And this is quite nice because they use a tunnel diode, and as it was said before, because in the end here we don't want to generate DC, we want to generate the second harmonic, but we are still relying on diodes. So the principle is the same as the ones that you saw with Professor Naoki before. You need a strong linearity. In this case, you don't want to have any DC, or at least you can take advantage of it, but you want to generate a second harmonic. And you can use a tunnel diode. In this case, they were biasing it, so maybe some work can be done to avoid this problem. But this means that for a certain power range, this tunnel diode works as an amplifier. So basically, you are decreasing the losses that you have for the harmonic generation. The solution that I mostly adopted so far, however, is based on a two-port frequency doubler. So this two-port frequency doubler is based on a diode. In this case, it is series connected. This can be also in shunt. And then here you have two harmonic filters. These are in microstrip technology. I don't know how many of you are familiar with that, but these stubs, they have a length of equal to a quarter wavelength at the interrogating signal. And it works like this. So when for the fundamental frequency, this stub here, which is connected, which is a short circuit stub, basically here is seen as an open circuit. On the other hand, this sub, which is an open circuit sub, the fundamental frequency here is seen as short. So the fundamental frequency that enters this frequency doubler basically only does this path. So here this is an open circuit, so it doesn't matter. It goes to the diode, and here it sees a short circuit. And basically this is a way to maximize the voltage that you get across the diode, so as to maximize the the power that you have, the nonlinearity that you can explore with your RF input signal, which is sinusoidal. And then here you have the diode. So basically the diode is generating all harmonics, including the DC and the second harmonic. But the DC, if you see here, it has a short-circuited path. So basically the DC voltage across this diode is zero, or in other words, this frequency doubler, in this frequency doubler, the diode is zero biased, to avoid the problem that was said before, that you can have self-biasing, and so the diode can become reverse biased. On the other hand, for the second harmonic, as I said, this is, oh no, I didn't say that. So this sub is, it has a length of quarter wave for F0, but at 2F0, it is half wavelength. So if you think of the Smith chart, basically you are doing a complete turn. So this means that here, for the second harmonic, you see a short circuit, and here you see an open circuit. So the path of the second harmonic is this one. So the second harmonic here doesn't go back, which is what we want. Here we don't want anything to go back to the source. And then it goes to the load, which is connected to this port. And then, of course, you need some input and output matching networks, because depending on the power that you have at the input, the impedance that you can, let's say, associate to the diode is different. And so basically you need to optimize which means minimize conversion loss for a certain RF input power. And in this case, the output matching network is also used, as I said, to provide a DC return. So to have this zero bias circuit. And here I reported basically how the conversion loss varies with the RF input power. As I said, basically you don't have a fixed conversion loss, but everything depends on your input power. And you can do your best, but after a while, when the power is very, very low, basically you are in the so-called linear region, and so you can see that the losses increases linearly in dB with the decrease of the RF input power. Okay, so basically I gave you the basics of harmonic tags. And an harmonic tag can provide you 1 bit of information for free. So this is something that you didn't have with UHF RFID tags, right? Because you can see them only if they are providing amplitude modulation. So they can provide you, let's say, a complete word at the cost of some power. Here you can have a structure that is completely passive. So it has only a diode, but it is only telling you, okay, I'm here. It is not that you need now to add some information on that. And this can be, of course, challenging if you want to do it low power. Here I'm reporting one early study on this that is very, very interesting, because basically this, I don't know if you're familiar with it, but this is the WISP platform that was developed by Joshua Smith. And this is for UHF RFID tags, but here it is integrated in a harmonic transponder. So the WISP tag works like this. You have an input port where you have basically you are harvesting RF power. This is the rectifier, and then you are basically switching on this microcontroller, and then basically this microcontroller is used to control, as I told you before, a switch. So basically, it is used to switch something on and off, right? Which was something that was needed for the UHF RFID tag. So here, this platform is added to our harmonic tag in this way. Here you have an input antenna, and at the beginning, all these switches are off. So here, this antenna is matched. So all the power is used basically to charge a capacitor, a supercap. And when you reach the enough voltage, this microcontroller is switched on. When it is switched on, basically both switches, switch A and B, are switched on. This means that this path is short-circuited, and so power doesn't enter here anymore. But this one, so the power goes here, and so here this is why you have a quarter wave transmission line. So this short circuit is converted in an open circuit. And here you have a switch that now is on, so here you have a connection. And this is the frequency doubler that is based on the nonlinear transmission line that I told you before. And the second harmonic is transmitted to this antenna. So basically, you are using this platform to give you some ID information, and then you basically control these two switches. And so first you get power, then when you have enough power you transmit signal, but not at the fundamental frequency, at the second harmonic. This was published in 2016 and is a very nice solution that was developed. However, also in this case, you need some power to switch on a microcontroller, and if you need to add sensing information, you basically can be in trouble. You might need an additional energy source. So, as I said, we are moving towards simplification, because this is the only thing we can do to avoid having any additional power source. And this is an example of a harmonic vibration sensor that was developed by my group. Here the idea, so basically this is the same scheme that I showed you in the first slide. The only thing, we added a block where we are doing a phase modulation of the second harmonic generated by the frequency doubler. And this phase modulation is controlled by some vibrations that we have in the environment. So the information is encoded in this phase modulation that is, as I said, caused directly by vibrations, because our goal is to have a completely passive transducer. And here is the system that we used to generate this phase modulation. So this part here is a branch line coupler, and the basic structure that we are using is a reflection type phase shifter. The reflection type phase shifter works like that. You have a frequency doubler, and then the direct and coupled ports are closed on capacitors. And basically the value of these capacitors controls the phase shift that you can measure between port 1 and port 2. The idea here is to replace the capacitors with varactor diodes. You know that varactor diodes are some capacitors, and by changing the voltage, the bias point of the varactor diodes, you can change the capacitance. But I told you that this is passive, so you may say, okay, how do you change the bias point? We did it using a piezoelectric sensor. So the piezoelectric transducer is providing the bias point, the variable bias point, to these capacitors and to the varactor diodes. In this way, we have a variable capacitance, and so we have a phase difference between the signal at port 2 with respect to port 1, which is a function of the voltage that we are generating. The setup that we developed basically to prove this idea, this is a shaker, and the accelerometer is just as a reference to understand which is the acceleration that we are providing to the system. And we used a commercial piezoelectric transducer from MIDE. Piezoelectric transducers basically works as mechanical resonators. So they have a frequency where you excite them at that frequency, they are providing you most of the power. And in particular, this piezoelectric transducer has a self-resonance around 130 Hz. So we studied it around that area. And as you can see here, it is connected to the bias port of this reflection type phase shifter. And here we made a wireless setup. So basically, this big box here is the signal generator. The signal generator transmits a signal to the input antenna, let's say the reader antenna working at f0. Then this power is received by the f0 antenna of the harmonic tag. Then you have the frequency doubler, and then you have the transducer. This is the 2f0 port. And then this signal is sent back to the second harmonic antenna that is connected to a spectrum analyzer. So very simple example. And first, we considered a fixed acceleration of 3G. So this is not really for, let's say, very sensitive application with very small vibrations, but it was basically to demonstrate the idea. And as you can see, so if I'm transmitting a continuous wave signal and I don't have any vibrations, the power that I receive is at the second harmonic, but it has only basically one spectral line. Once we apply these vibrations, we are basically seeing all these sidebands, which are a function of the phase modulation that we are providing with the phase shifter. And as you can see, basically, if you change frequency, things, this second harmonic is decreasing quite rapidly. So we have a very, peak at the 120 Hertz. So the point is we need to calibrate the system in advance. This is not linear. But anyway, if you want, for instance, to understand if the system is vibrating at the correct frequency, or if there are deviations, for instance, due to some, let's say, when with time you have some aging, so things are not properly working as probably a good solution. And but once you have characterized it, you can use. So for instance, the frequency, the vibration frequency is encoded in the frequency difference between the carrier and the sidebands. So this distance here is equal to the vibration frequency. And in this case, basically for a fixed acceleration, you have different amplitudes. So you have to make kind of calibration at the beginning. And however, once you have calibrated your system, for instance, if we keep the vibrations constant, and you can retrieve the acceleration information from basically the modulation index of this system. If you consider the ratio between the power here and here, you can see that when you change the acceleration frequency, you have a change of this modulation index. And by the way, you can do this because you are working at the second harmonic. So this power here is not affected by the environment, it's only generated by your frequency doubler. So this is a robust information that you get. Okay, the same principle that you applied for vibrations can be applied also to temperature sensing. But in this case, of course, we are not generating any modulation because we don't have a periodic signal. We only have temperature that is changing, usually slowly over time. So to retrieve this information, basically we complicated a bit the reader that you have in mind. Oh, you either have to, one possibility is you want to retrieve this phase information, for instance. You can do it if you have a receiver that is coherent. The point is that the phase difference between the F0 and the 2F0 signals can also change if you change the distance between the tag and your reader. So to make the information more robust, we complicated a bit the architecture. And the architecture works like this. This is only the tag. So you are receiving the F0 signal. This signal is doubled in frequency. So here you have the second harmonic. And then you have a power divider. So you are dividing the power into parts. One part is just transmitted towards, with an antenna in vertical polarization, and the other half is phase shifted with a system that is similar to what we saw before in horizontal polarization. And basically, if reader as an IQ receiver, you can retrieve this information from the ratio, basically from the ratio between the phase difference, between the signal that is transmitted in vertical polarization with respect to the one that is transmitted in horizontal polarization. So we basically added a power divider, and we need an antenna that has two ports so that we can transmit into orthogonal polarizations. This is the variable reflection type phase shifter. Basically, it's very similar to what we saw before for vibrations. Again, we have a branch line coupler, and the direct and coupled ports are close to two identical capacitances, so that by varying these capacitances, we are changing the phase shift between port 1 and port 2. In this case, though, we are implementing these capacitances using some parallel plate capacitors, which consists of basically this. For each of the two ports, you have two contributions. One is this pad here, then you have a dielectric, and then you have another metal pad, which consists of a bimetal cantilever, which short circuits all these pads. So basically, you have a capacitance that goes from pad to this cantilever, and then from the cantilever to ground, because here this pad is connected to ground. So basically, you have the series of two capacitors. And this circuit is really inexpensive. We made it on FR4, also all low cost. And in this case, to demonstrate the idea, we made it work around 2 gigahertz. So how the a bimorph cantilever works is that it is made of two metals that are stuck together, that has a different thermal expansion coefficient. So when you are changing temperature, basically the cantilever bends. This is the basic idea. And so by bending, you are basically changing this capacitance contribution. To avoid short circuit, when they are flat, they are in touch. Here we put also a mylar layer. So basically this is, when they are basically trying to touch each other, there is a minimum distance between them, which is the thickness of the mylar layer. But then when this cantilever deflects, this distance between the pad and the bimorph cantilever increases. And basically this means that the capacitance decreases, and so you have a variable capacitance in a completely passive way. And here we also created a model for this capacitance to describe how it changes with temperature. And this is the prototype that we made to demonstrate our idea. This bimorph cantilever, it was not made on, by us on purpose. Basically, when one person of the group got his, how do you say, I don't know the name of the heater, I think, that you have at home, broken. And so basically by trying to adjust it, he understood that this bimorph cantilever is part of it. Basically, when you set the temperature, this is used when temperature is reached, to switch off the the heating system. So it is really used with common stuff. And we made a test in a climatic chamber. So we kept constant humidity, and we varied temperature from 25 degrees Celsius to 50 degrees Celsius. And we measured the S parameters of this circuit using a vector network analyzer. So as I said, this is the phase difference of the transmission coefficient between port 1 and port 2. And you can see that up to 30 degrees Celsius, there is no phase difference. This is because the cantilever would like to bend in the direction where it is not possible because there is the PCB. So the PCB is rigid, it would like to bend on the opposite direction, but it cannot. So it stays there, and the temperature and the phase difference is constant. But after a certain temperature, you can see there is a significant phase variation. Also in this case, this sensor is nonlinear, but you can have a very significant change, for instance, between 30 to 40 degrees, where you have most of the variation. But in this range, basically, you have a variation of about 47 degrees. So it's really, you can really retrieve this information wirelessly in an easy way. And then we used the same architecture to build a very simple crack sensor. Other people try to do the same thing. So there are other solutions where, for instance, crack sensor is retrieved towards some breaks on antennas. In this case, we put a filter between the input antenna and the frequency doubler. The idea here, so this is a stub, as I showed you before. This is an open circuited stub, which is a quarter wavelength at f0. This means that for the input signal, this is a virtual short circuit. So all the signal that is gathered is basically, it goes only there. And when the filter is there, we don't receive any second harmonic, or at least a very, very small one. On the other hand, if this stub is turned off, so if you break the tag, then the signal can definitely reach the frequency doubler, and then you get basically an alarm. It is telling you that you have that something, that your crack is increasing, and so you have to basically check. And so we can model this as a system where you have a conversion loss that is changing with the status. You have two possible conversion losses. And of course you can put this tab also at the output, and in that case you would have to make it a quarter wavelength at 2f0, so you can make a short circuit here. But we put it the input because maybe you remember that the conversion loss is not constant with the available input power. So if we put it at the input, you basically increase the conversion loss because maybe you are in the linear region, and so you can create a very big dynamic range between the two status. We made a tag, so to make it breaks easily, we made it on paper substrate. So this is so that you can tear it quite easily. And this is the tag. Also, to make it very compact, we use these slot antennas, annular slot antennas, which are long, one wavelength at the operating frequency. So we basically leverage the fact that the second harmonic is higher, so the antenna is smaller, to put the second harmonic antenna inside the F0 antenna. And then since there is a kind of the electric field here as a pattern where you have the maximum of the electric field here and here, we also put a short circuit so that basically all this is the ground plane for the microstrip line circuit that is on the other side. So basically it works like this. This is the input antenna. This is coupled electromagnetically with the microstrip line that is on the other side by using this disc stub. This is the filter that I told you that is used to short circuit the fundamental frequency. And this is the frequency doubler, which is based on this low barrier Schottky diode, and the circuit is made to make it zero biased. And then the signal is sent back with through the other, the second antenna that is working at 2f0. And the graph here on the right side, the part, the one below, is showing the received second harmonic versus distance. And we were transmitting 25 dBm of power, so we could be we could have transmitted more power according to regulations. But anyway, so this is the received power in a normal environment. We were in the lab. Of course, the point is that your receiver has a certain noise floor. So since if you go farther, the received power when there is an alarm decreases, there is a point where you cannot distinguish between these two conditions. However, we were able to measure a difference in the let's say dynamic range between the transmitted and received the received second harmonic for the tag intact or broken of about 50 dB. So it's a very big dynamic range. And this sensor is very lightweight. It's based on paper, so it only weighs 3 grams, which can be nice for some applications. Okay, then we also worked on another possible architecture. As I told you before, we made, basically we use this inductor here to create a short circuit so that the diode is zero biased, which is the best we can do to maximize the conversion gain, or in other words, minimize the conversion loss of the system. But then we thought, okay, we might put here a MOSFET, an NMOS transistor that can work as a switch. So when the switch is off, this is an open circuit, and so here the DC doesn't have any return. So we demonstrated in this paper that this means that a positive voltage is developed here across this bypass capacitor. And this means that the diode is reverse biased because this part here stays at 0, is fixed to stay at 0. So this means that the second harmonic that we generate is less. On the other hand, if here we applied a signal, this is closed. If you apply the voltage, which is above the threshold voltage of the MOSFET, then this is a short circuit. So basically, this is a DC return for the self-bias component. And so we are in the previous condition. So basically, we have the maximum power, RF power at the second harmonic. This way we can achieve an amplitude modulation of the signal at the output port. And this solution has some advantages because, for one thing, we don't have static power consumption. We only have power consumption to charge and discharge the capacitance dynamically. And the thing is that we are working on the DC component of this RF circuit. So basically, this solution is very insensitive to parasitics, which can be a very nice thing if you want to use this approach not to transmit data, but for instance to transmit sensing information. So, but first of all, we characterized and we try to understand, okay, but how much dynamic range can we achieve between, the conversion loss when this MOSFET is on or when the MOSFET is off. We made some tests. So this is a frequency doubler, again made on FR4, so very low cost solution. And for MOSFET also we use a very common MOSFET with an N channel, which is the BSS123 model. And basically we applied a voltage of 3 volts when we wanted to have the on condition and 0 when we wanted to have the off condition. And here we reported the conversion loss versus RF input power in the two states. As you can see, we achieved a maximum on-off ratio of 23 dB, which is very high. So basically we can discriminate between these two levels quite well. Of course, when we decrease the RF input power, this difference decreases because basically if you have less RF input power, basically it's also less, you are getting also a smaller DC voltage, which means that your bias point in the reverse bias is closer to 0. So but at the end, we could have a difference of about 9 dB even at minus 20 dBm, minus 25 dBm of RF input power. So it could be fine for these applications. And here we made a test, a wireless test. This is the same setup that we saw before, and this is the tag that we, for now, is not complete. Is composed of different pieces. The F0 input antenna, the doubler with this modulation port, and the 2F0 antenna. And in this case, we applied, let's say, a square wave signal, and we were able to read this, we were able to measure a spectrum which is compatible with square waves wirelessly up to 1 megahertz. So we are applying a square wave voltage, and we are reading this information wirelessly using a spectrum analyzer, and we were able to determine the very same spectrum up to 1 megahertz. So this is also applicable to high-speed communication in principle. But as I told you, in my research, we don't want to use active things. So, okay, this is a principle. How can you apply to sensing? And the idea is, for instance, okay, but what is a MOSFET used as a switch? Is a variable resistors. So why don't we put some variable resistor here that is giving us some information about sensing? And in particular, here we made used this configuration to realize a harmonic pressure sensor. And in particular, we implemented this variable resistance with a piezo resistor. We used a commercial material, which is 3M Velostat. I don't know if you've ever seen it. It seems really similar to the material that is used for the bags for your trash, because it's really thin. But the nice thing is, if you apply some pressure on it, you can see that the resistance that you measure across it is varying. In particular, this resistance decreases when you apply a pressure. Okay, and here we can see that it is behaving linearly in terms of, so the conductance increases linearly, and this is the of course, resistance, which is an hyperbole. And this is the test. I want to stress that we can make this with an RF circuit because we are working on the DC bias, on the self-bias, on the DC. So we are only, let's say, impacting on the DC. Because as you can see, we basically we connected this transducer to this frequency doubler using 2 wires, which would change dramatically the behavior of the system if this would have impacted on the 1 gigahertz signal which is used for interrogation, or the 2 gigahertz signal that is the second harmonic that we are receiving. Anyway, we varied the applied pressure. As you can see, also we made we used some copper tape, and we used some plastic tape to make the system together, and then apply some pressure. And we could see a variation on the received second harmonic of about 8 dB. And then we decided, okay, we can use maybe something even different. Instead of having a MOSFET, we could use some different switches that are usually, too big. They have too many parasitics to, maybe be used at RF applications. And in particular, we used a reed switch. A reed switch is an electromechanical switch which is activated with a magnet. So if the magnet is closed and is nearby, the switch is closed. If there is no magnet, the switch is open. And we basically put it in the same place that was of the MOSFET before. And of course, this is really important. Here we added a bypass capacitor. So basically, the RF signal only goes here. There is no RF signal impacted by that. And this is the preliminary test that we made. This is the reed switch that I told you before, that is used maybe in industrial applications. For instance, if you want to understand if your machine went till the end of the path, Usually you can find it in industrial applications. And we could see the same variation in the conversion loss as the one that we obtained with the MOSFET. Then, okay, we decided, okay, maybe we can use it, for instance, to measure, because we, if we want to make a modulation, we always need some periodic signal. So we said, okay, maybe this one can be used to monitor the rotational speed of, in this case, we used an electric motor. If you want to make the measurement of this rotational speed, we could use this solution. So this is this metallic rod that is rotating over time, and we put some magnets on the border of this rod, and nearby we put this switch, as I told you, and here you have the doubler and the and this is the signal that we got. We got, this is the carrier frequency, and then this is the sidebands. And the distance of the sidebands is about 40 hertz, which was which corresponded to the rotational speed of this. Actually, it is 4 times because we put 4 magnets, equispaced magnets. So the rotational speed was 10 hertz. And this was this speed was confirmed using a photoelectric sensor. But the nice thing is that this solution, so usually you use photoelectric sensors to understand the rotational speed of this stuff. But in industrial applications, might be not always possible because, for instance, you can have environments where you have a lot of dust, a lot of, debris. And so maybe optical solutions cannot be always a solution. And so this can be a different approach. And again, it is completely passive. And the nice thing is that you can put the reed switch here, and then you can use wires. And your transponder that has to transmit information can be farther away because you are working with the DC component. And so even if these wires are longer, this is not really impacting the behavior of the sensor. And finally, I think this is the last example that I was bringing here. We applied this solution again to, let's say, this circuit scheme, again to perform a vibration sensing. Again, here we put a switch, again a MOSFET with an N channel. But instead of providing the bias to the switch, instead of switching the gate port on and off using, let's say, a microcontroller or something similar, we used a piezoelectric sensor. So piezoelectric materials work like this. So they are crystals usually. I don't know if you have ever had the experience. The most famous one is the PZT material. And when you try to deform them, they basically generate a voltage. So they are used, for instance, as energy harvester, because if you apply, as I showed you before, if you apply the periodic solicitation, you get a sinusoidal signal, and you can harvest that also for power. In this case, we used it for sensing, but we used this piezoelectric transducer to basically control the gate port of the MOSFET. And usually you don't harvest a lot of power, but the fact that we use the piezoelectric material to, let's say, drive the gate, it was very beneficial because the input impedance is very high. And so even if the power is not that much, but the voltage that you get is enough to switch the MOSFET on and off. And the idea was this one, basically. So usually, vibrations are sinusoidal, but the switch is on in a threshold way. So basically, if you are above threshold, you have the switch on. If you are below threshold, the switch is off, and so forth. So how can we measure the amplitude variation? The idea here is that, of course, if you have a stronger signal, higher, if this voltage is bigger, then basically the fraction of time for each period where you have the switch on is higher. While if this signal is weaker, basically this time is lower. So basically you can retrieve the information of the amplitude from the duty cycle of the backscattered signal. And this is shown here. Basically, this is a spectrum, and this spectrum is the spectrum of, in this case, I think it's a square wave with a duty cycle of 20%. So basically, the frequency is retrieved again, in the difference between the frequency of the carrier and the frequency of the first sideband, for instance. And then the shape of this signal that is retrieved with the spectrum analyzer is a function of the duty cycle. Usually, to recover this information, we need an IQ receiver, but here things can be made even simpler because we understood that the maximum duty cycle that we can have is 50%, because here we have a sinusoid, so for half of the time we are for sure below threshold. And if we use that, basically we can recover the information on the duty cycle only from the magnitude difference between the second and the first sideband. So basically you don't even need an IQ receiver, which is of course good. You can use it to recover this information, but you might also use a spectrum analyzer or only get information on the magnitude of the received signal. And this is the setup that we used. Again, we have a signal generator, we have a transmitting antenna for the reader, we have a tag, and this is the receiving antenna for the receiver, which in this case is a spectrum analyzer. And this is the tag of the antenna, and there is also the frequency doubler. Again, we only have one component. And then we connected the transducer to this to the MOSFET that is below, to the gate port of the MOSFET using two wires. And this is the transducer, this is the shaker that is used for the measurement, and that's it. This is the same as before. And these are the data that we received. So again, since we are using low power solution and passive solutions, we have all the time this drawback. The sensitivity is not linear. So this is how the acceleration. So this is the acceleration of the vibration, and this is how it impacts on the duty cycle. So of course the duty cycle is not changing linearly. But anyway, we have now a significant range of variations. And here we are showing that this duty cycle that was estimated for given distances is the same as also varying distances. So this information can be retrieved wirelessly. And this is, for instance, one of the signal that is received by the spectrum analyzer. And then this is the signal envelope that was recovered using the information that I told you. So basically just considering the ratio between the second and the first sideband. And of course, here you don't have perfect square shape because we are using a limited number of harmonics. However, this is the normal shape that has any signal that is recovered from its Fourier series. And as I told you before, harmonic tags are really robust to clutter. So for instance, here we put a metal plate between the antennas and the tag. And of course, if you put a metal, so basically you don't have a line of sight, the power that you receive is lower because you have less power that reaches the frequency doubler, but still the information, of course, because we weren't close enough, otherwise you might get the power that is so low that you don't get it, but this is for all systems. Anyway, the information that we received was the same as with no obstacles. We also put a fan, a metallic fan rotating in front of it. Of course, the speed of the fan was much lower with respect to the vibration information that we were measuring. But what we observed is that if there is an obstacle that is also moving in front of the tag, but is moving at a speed that is much lower than the vibration that we want to retrieve, of course, this is not impacting on the reading. And I also wanted to, so far I always show you things that were tested in a lab environment, which may, which can make you think that harmonic tags we need for an expensive reader. But in the end, you can actually use very low cost solutions. In this case, I used software defined radio, and that I connected. So this is the Adam of Pluto. I don't know if you ever worked with that, but this software defined radio has two channels, one transmitter and one receiver, which is exactly what we need. And one port can be connected to the F0 antenna, and the other one can be connected to the 2F0 antenna. And so basically, this is very simple because we only have to transmit a sinusoidal signal, and we only need to measure the spectrum of the received signal. The point with that I mentioned before, or only briefly, and that is let's say a weak point for software-defined radio, is that of course everything works perfectly if your generator is a good generator. So if it's transmitting, if it's generating a sinusoidal signal which has only the spectral line at f0. But what if you have a signal that is generating by itself a second harmonic? Well, that one is not a big problem because if you have a transmitter that is separated by the receiver, you can put a filter, and I did it in my previous solutions. You can put a filter so that even let's say a low pass filter, or even you can have a notch filter that eliminates your second harmonic, that it's the spurious second harmonic of the generator. And that is no problem. But in a solution like this one, you sometimes have some internal leakage, and that one is a little bit more tricky. So here the idea is to use this software-defined radio at a very low power, basically just to give us the carrier, and then here we use an amplifier at the input, and here this one is a filter attenuating the second harmonic, and here at the receiver you have an LNA. So basically we are improving the sensitivity of this system, but this one again they can be powered with a power bank very easily. And this is this tag that I have here with me, so if you want you can also see it. Basically the tag is all antennas, so I can also make it smaller, or I could play a little bit, but in the end there is the input antenna, there's the frequency doubler, and the second harmonic antenna, and then here you have the sensor. In this case, instead of using the MIDI sensors, this one is used for guitars. I bought like 30 of them for 20 euros or something like that. And they work, they are piezoelectric. So they work like this. If you apply a voltage, they create a sound. You can try them. If you apply sinusoidal voltage to them, you can hear a sound corresponding to that frequency. But if you deform them, you generate this voltage. And I can show you this video. Basically, I'm not very well coordinated, so you can see that it's not. It takes me some time to get it to take it with my camera. But the idea is that you can see that there is a spike every time that I push it, because when I'm not applying a pressure, the conversion loss of the frequency doubler is very low. So basically, I only see the leakage of this tag. But when I apply a pressure, when I apply a pressure, I'm basically closing the switch. So I'm making this frequency doubler work at its best, so with the minimum conversion loss. And this works like a flash, basically. You can see that you can have about 20 dB of variation in the second harmonic that you're receiving. Oh, wait, okay. And that's it. So basically the goal of this presentation, that I think will give us some time back, but I think that it has been a long day, so it's okay. So I provided you an overview of current recent advancements on passive harmonic transponders, which doesn't mean that they are passive, but means that you are providing RF power, basically. And they are based on similar principles as the ones of rectangles. The point is that here you don't want to generate a DC, you want to generate a second harmonic, but they are basically they are facing similar struggles. And we are also trying to avoid basically adding microcontroller, which however would make our life easier because you know if you have to digitize an analog signal, you need some power, and sometimes this may limit the read range of your system. So we are trying to see how far we can go, basically only. So adding some vibration sensing principle, temperature sensing, pressure sensing, and I also show you an example of rotational speed sensing. And yeah, our idea is to develop, to open the door to a new class of passive wireless sensors that can be robust, operate in harsh environments for diverse IoT applications. So I thank you very much for your attention, and I'm open for questions. Are there any questions? No, maybe. If not, well, go.
Just a comment, perhaps. Have you come across any instance in which the backscattering from certain objects generated harmonics? What I'm alluding to is, can backscattering occur from non-linear?
Sure. Sure. Well, I'm not really an expert of how to, of the materials and this kind of stuff, but I think that this is basically the how everything started, with RFIDs and everything. So everything that is non-linear, but most of the things, the environment is usually linear. And personally, I didn't have an experience where I could find something, non-linear that was masking my tag, if this was the question.
Yeah.
But of course, if you might have some materials that maybe they don't, I don't know, they don't just, they might, I don't think singular material, but you can have some junctions, basically. And if there are some junctions, then they can also create harmonics. This is for sure.
Any natural occurrence of junction can behave like non-linear scattering?
Honestly, not that I know, but maybe some semiconductors and some electronics.
You can actually have it, but you need a lot of power.
Yeah,
But it's
also.
not unique. Like,
Yeah, you're right. So if you have a lot of power, maybe the material doesn't behave anymore as linear. Yeah.
Well, there are some people that are exposed to humidity. You can have, but you need a lot of power to actually excite those.
Yeah.
Perhaps another question which occurred was when you're talking about MOSFET as a switch, at one stage you pointed out that in order to avoid trouble with harmonics, you replaced it with a conventional reed switch.
Oh no, not to avoid having troubles with the MOSFET works perfectly, very well, because in the end you only need a variable resistance. So basically, if you the MOSFET works that if I am applying a voltage above the threshold voltage, I have basically a very small resistance in the path between drain and source. And on the other hand, if I'm not applying any signal, I have a very high resistance between drain and basically I have no channel between drain and source. What I'm saying is that a reed switch usually cannot work at RF because it's very big and it has a lot of parasitics. But here we could apply it to a system that is working at RF because we are basically trying to, we only impact on the DC return. So we are only basically changing the DC that is self-generated by the diode. So we can also, we tried, we said, okay, let's see if we can do this. And we understood that we could. So basically, we are obtaining the same conversion loss, so the same second harmonic with a MOSFET or with an electromechanical switch like a reed switch. And this is good for sensing because it gives us more possibility to implement that switch.
Just one last question.
Sure.
And I'll leave you in peace. Now, you mentioned two situations. In one which the antenna was short-circuited, and one in which was connected to a matched load. Yeah, can't remember which slide, but at least in one of the slides.
You mean the crack sensor?
Yeah, could be. Yeah. You were looking at you referred to the behavior of the antenna when it was short-circuited and when it is connected to a matched node. There was a situation somewhere.
Oh, well, maybe this is at the beginning about.
Beginning, correct.
Yeah, this one maybe.
Yeah.
So the.
So my question is, I'm told that when an antenna receives any signal, it radiates the same amount of signal in space.
Okay.
Am I right in believing that, first of all?
So, no, I think.
I was told that no antenna can receive any power without re-radiating the same power back into space.
So the point is here is that, of course, if your antenna is matched, some of the power must go to your load, right? Okay. If it is short-circuited, all power is reflected back. So the point is you are achieving an amplitude modulation. And this is where your information comes from, because here you have some zeros and ones that you want to transmit. And you want to do this without having any carrier on board. And this is the basic principle of UHF RFIDs. So the idea is that even if you are re-radiating something, because even having the perfect match is very difficult, and I must say that even in this case, your RF input power is a function of the RF of the power. Sorry, your matching is a function of the RF input power. So maybe you are not always perfectly matched. But however, the importance is that the power that you backscatter when you have a short circuit is much higher than what you backscatter when you have a matched load. And this gives you the possibility at the reader side to recover this amplitude variation and so the information that was basically conveyed. I hope, yeah.
Thank you very much. Very clear.
Yeah, you're welcome.
Very clear explanation. Thank you.
So, of course, this is something that, in my research I was not exploring this solution, but this of course is much more versatile, because if we could basically use the RF power, the RF signal, both for, with the wireless, with our antenna, and having a microcontroller that gives you, that you can program and gives you all the information on sensing, this can be great. And there are some commercial solutions that are very low power at least, but the read range so far that I could see was very limited. So you have to be very, very close. But still, I think that there is a lot of research, and if you are going towards low power electronics, this can be, of course, a very nice solution. Using a microcontroller to get the information and then have this string of bits that is just transmitted at the second harmonic, so that you don't have any self-jamming issues. If there are no other questions, I don't know, I think we can maybe close the session.
So let's thank Valentina again. I just want to say that I think the organization is going to send you an email with a Google form if you can fill it out so that we know next year what we could do in terms of this school. So thank you very much for coming. I hope you like it and feel free on that form to put your comments and throw your discussions there for future schools. Thank you very much.
Smoke past the pipe and the air conditioner